Doran Swade is our chairman, is at home, is watching, but is not able to be with us. So let me just start by saying next month is the Christmas film show, and we're grateful once again to Dan for organising that. That will be hybrid. So if you want to come and share your reminiscences of the various clips that Dan will be playing, if you want to come here and share them, you're very welcome. But it will also be put out via Zoom in the normal way. So the choice is yours, but there will be a meeting here if you'd like to come. And then in January, we have a Zoom only meeting, and it will be at 9:30 a.m. in the morning, when Derek Brown from Australia will be talking to us about the birth of the barcode. And in order to accommodate the 10-hour, I think it is, difference in the time zones, it's 9:30 here, and it will be 10 hours forward from that, 7:30 in the evening, his time. So that's January. So January is a Zoom only meeting, but the Christmas film show, you're very welcome to come here. I think that's sufficient. I'd now like to welcome Bob Eager, who's our speaker for today. Bob is going to talk about the Edinburgh Multi-Access System, which I know some of you present know a good deal about already, and indeed have been users. I also had a sneak preview at Bob's speaker's notes, and I noticed that slide number 2 said, "Who is Bob Eager?" And since Bob has a slide and is far better informed than I am as to who Bob Eager is, can I at this point invite Bob to tell us about himself and his career, but in particular about the Edinburgh Multi-Access System. Okay. Bob, over to you.
Thank you. And if Bill notices I'm fading away, just let me know. Right, okay, so good afternoon. Thank you first of all to the CCS for inviting me to give this. Hope you enjoy it. Computer conservation is about software as well as hardware, and this is a pretty well entirely software thing. Special hello, by the way, to anyone from the EMAS team who's attending, probably on Zoom. I know there are at least 1 or 2. The parts concerning the 2900, which is quite important in this, are mostly from my personal experience. The rest I've researched or I've asked people and so on, and I've cross-checked it as much as possible. If there are errors, they're mine, but I have done my best. The slides are probably more informative, and there's more on them than you might wish in some ways, but they're there because I've had experience of students not having textbooks, not writing stuff down, and so more of the stuff goes on the slides, so to give them a prompt. The slides are going to be on the website, which I'll tell you about at the end, and of course the video is also going to be happening. You may be asking why somebody who isn't even from Edinburgh is actually, oh, I've got it. How do I get rid of that? So I'm on here, yeah, it's yeah,
you don't, you just need to click or anything.
Okay, I wasn't sure that was coming from the other.
Yeah,
okay, right. Okay, so no, which button is it?
Left and right, but it's
no.
Should be working now.
That's it, right, okay, good. So I graduated in electronics from the University of Kent in 1973. I wasn't very good at electronics, but I got a bit better at computing. I did a Master of Essex in 73, 74, and then I went back to Kent as a research student. I didn't have enough funding, so I became a part-time programmer, and I helped support VMEK on the 2900, and it arrived in 76. I implemented the IMP language, which you'll hear more about later, on the PDP-11, on DOS 11. So I was the first person to have experience of it, really. I had the choice of going off to go and to work for people. I was offered a job by ICL. I was also offered a job by IBM. And my final year project was modifying a CPU, which was great fun, actually hardware modifying it. But anyway, so I became a lecturer and then a senior lecturer in computer science at Kent in 78. And I went on doing that until 2015, the eternal academic, when I retired. And I still go back and give the occasional lecture. I managed the Kent EMAS system from its very first installation in April 78 until it ceased in December 86. And I was able to do this because my director was quite happy for me to spend 50% of my time doing that and 50% doing teaching. So that was great. Right, so some basic information about what EMAS is. What is it? An efficient, as it says, a multi-access system, which they needed at Edinburgh, offering interactive facilities. They already had batch, that was okay. And it was on ICL mainframes of various sorts, and then IBM and clone IBM mainframes as well. And the dates for this were from 1970 rather. There was some stuff before that, but that was just development. It wasn't actually something that carried on all the way up to 1992 when they finally shut it down. The PC and so on were taking over. Where mostly the University of Edinburgh, but at Kent we did do some development. The system development was entirely by me, but there was other development going on. Kent provided a lot of software and so on. Okay, so going back to the history, which is the important thing. Am I pushing the right button here? Yes. That's it. So 90s. I've got something overlapping my slide here. Can that be changed?
No, yeah, sorry about that.
Yeah.
There we go.
Yeah, that's okay. That's fine. Good. So 1966 was important for University of Edinburgh because that's when they founded the Regional Computing Centre. And that was for the region, which certainly included Glasgow. I'm not sure about the rest. And they rented a KDF-9 to provide what was essentially a batch service. And it supported Atlas Autocode. And for those of you who don't know, most of you probably do, it was a high-level language. It wasn't what I always used to consider an autocode, sort of assembly-like. Essentially, Algol 60 with the difficult bits taken out and some other stuff added in, particularly things like call by name and the way Algol did it. And in the same year, they had a large team from Edinburgh and from ICL, because we'll see why in a moment. They wanted to write a multi-access system, and the project to do that was for the English Electric Leo Marconi. We all know it as a System 4, don't we? System Sub 475. And Harry Whitfield from Newcastle, who was later at Newcastle, did this. I'm very much afraid that Harry may be watching today, and so he'll no doubt call me out if I get things wrong. And they developed a language called IMP as an implementation language, which was really Atlas Autocode with some nice bits added on. And it drew on work from the Brooker and Morris compiler back in the day. And it was one of the very few systems that was implemented in a high-level language. We had, of course, Unix in C, which was coming along, and Multics in PL1. But the important thing, of course, here was that they were using IMP. And it had a lot of people in it, probably too many, as you can see, about God knows how many people in total. But so I mentioned IMP already. And System 475 was delivered in December 1978. And so September 68 and June 69. The disk came later because it wasn't available. And it didn't really go very well, this development. The KDF-9 had gone, they had nothing else. And sorry, there's something else here, Darwin. Can I get rid of that bit? There's a reason. That's it.
Yeah, let's see if I can get rid of it. Okay.
I've got something coming up in that corner, you see, so I need to have.
Zoom is very good.
Okay. So they abandoned this project because it just was only providing support for a ridiculous small number of users, probably about 10, and the response time would have been terrible. So they started an internal project on EMAS, just the Edinburgh people, and they got a service going within a year, and they called it EMAS. Previously, it was EMAP, the project. And they started a formal service a year later, and it supported 35 to 40 terminals. Now, these were serial terminals, of course. We're talking back in the day, teletypes, not even very many VDUs, I don't expect. And they handed over the project to Edinburgh Regional Computing Centre. Prior to that, it had been a mixture of the Computer Science Department and Edinburgh Regional. And the system was really popular, and it got overloaded very quickly. And they modified it and improved it because they'd done a very quick implementation. And so the idea was to try and get as much out of it as they could. But eventually, they managed to get a Seconds 475. How they swung that, I don't know. But the director, Tommy Thomas, was probably he was very good at that sort of thing. So they needed a replacement, and they were basically told by the computer board, you can't have a non-British system. It's all going to be British. So you can't have IBM, so you're going to have an ICL machine. It's one of the new range machines. And I expect there were groans at the time because it wasn't ready and everything else. But it was going to be a 2980, which was the super beast version of the 2900 at that time, running about, in modern terms, about 2.1 million instructions per second. And it had to be running VMEB, which of course was the ICL system. But that was okay. It was delayed, the whole system was delayed, as I said. So what ICL said was, well, look, we'll give you a stopgap. We'll give you a 2970, which is about 30% of the power. And the 2970 will have to do for now, but the memory wasn't very much, a megabyte. And that supported a batch system fine. And one or two interactive users, which wasn't actually what it used for. So ERCC were trying to do their best at getting throughput, and they had a lot of good compiler people, two in particular, and they produced Algol-E and Fortran G compilers, and of course an IMP compiler was also there. And they produced something called the Scientific Jobber, which was written in IMP, and the Scientific Jobber was essentially a program that you ran and kept running, and you just fed card images into it, and what came out was your run program, Fortran, Algol, whatever. And it ran in memory, so the compilers were resident, it ran the program, threw it away, did the next one. So it was quite fast, but there still wasn't enough happening there. You know, it just wasn't good enough for interactive work. So then the EMAS team said, well, look, come on then, can't we do something about this? And they said, we could get EMAS going on this. But by that time, they were moving towards a network, and the network needed to have some kind of interface to the machine, which they hadn't really managed up to that point. And that's what they did. They found a way of doing that using a PDP-11 as a front end, and they connected it to their network. So the 2900 was actually quite a good architecture for this. It was good for doing IMP. And so what they did was say, well, we'll implement it in IMP, obviously. Easier to do in the IBM because of the way the machine worked. And they did a paper about it. Well, they did several papers. But the one I love with the title is an experiment in doing it again, but very well this time. And that's exactly what it was. It's a good paper. It's available via the website I mentioned. EMAS 2900. And we also later called it EMAS 2 for reasons you'll see. So they've got a pilot service going, and it's already 30 terminals straight away, which is great. And ICL eventually donated that 2970 to ERCC. I don't know what they would have done with it anyway. And they offered a full service from October 78, which was quite interesting actually, because that was around the time, April 78, that Kent decided to have a go. Why did we do that? Well, more about that later on. We hadn't realized actually how early in the development cycle we were. They'd only be running a service from October 78. We got it installed to try out back in April 78 before it had even gone live. I had no idea at that point that's what had happened. So yes, probably just as well I didn't know. So by October 78, the 2980 was supposed to meet its benchmark. In fact, it should have been a year earlier, but they got the 2980 a year late. And that year late was because it went to a preferential customer. And they had another one. but they had still had to adopt the 2980 for regional service running VMEB, and they weren't really very happy about it. So nothing much they could do. It just at that point there were no other options. Eventually, somebody managed to convince the computer board that they could run EMAS on it, and that happened in January 1980. And it was not without its problems. The 2900 range at that point was notorious for range incompatibilities. The way you programmed at the system level using something called image store, the image store addresses were different or worked differently on practically every machine in the range. And so it had to be tweaked. But they did that, and they did it in January 1980, which is actually 2 weeks after Kent changed. We changed on the 16th of December 1979. So yeah. The 2970 and the 475s got replaced by 2972, which is a dual. They added 2 distributed array processors, which were integrated nicely into EMAS, and then they replaced that with the 2976, which is a bit faster. The 2980 got upgraded to 2988, and so yes, it all moved forward quite happily. But that was really the end of the ICL era. There were no more ICL machines coming through. And that would have been about 1984. So in 1984, they got an Amdahl 470 V7, which is an IBM mainframe clone. You probably all know that, but with some changes. It's got 31-bit addressing instead of 24-bit addressing, which was something that EMAS wanted for reasons, again, that we'll come to later on. But it's got conventional channel hardware. It hasn't got the new XA type channel hardware, which is a bit more complex. I thought this was quite ironic, actually, for a couple of reasons. One is that all they did was swap one shade of orange for another by getting the Amdahl. And the other thing was that they'd replaced the 2900 with what was essentially a Fujitsu machine, because Fujitsu had got Amdahl by that time. And what happened to ICL? They got absorbed into Fujitsu. But by the spring of 85, they got it running, a re-implemented EMAS, and we called that EMAS 3. Hence the EMAS 2 thing. And they ran that for several years. Now this is where it's a bit hazy, because there's very little information about the next bit. But Kent were having a go all the same at improving EMAS 3, because we wanted to carry on running EMAS when our time ran out in 86. And the idea was that we'd get it running on a 4381 IBM. And that's a 31-bit machine, but a proper XA machine with the sub-channel subsystem. So I spent a lot of time getting that working, and I was taking a mag tape from Canterbury on Monday mornings up to Greenford, where they had a machine I could use, and then coming back with a dump tape, and then going back on Wednesday, having spent Tuesday looking at it, and then doing the same on Thursday and Friday. So I did 3 trips a week. But IBM, and it worked, we got it working, but up to a point where we knew we could do the rest easily. But the IBM tender was unsuccessful. They had some very inexperienced people actually handling that particular account. We got a VAX cluster instead. That was just unbelievably problematical, not to do with DEC, but to do with some third-party stuff. And so we stopped running EMAS at Kent in December 86. But more about that later. So by mid-1988, they managed to get another machine, and it was, depending on which period you look at, ITEL Nassau Hitachi, a VL80, which is one of their more powerful machines. A 15 MIPS processor, dyadic, which is quite big for the day, 64 mega memory, enormous, more than 40 gigabytes of disk storage, we'll wonder at that now, and 8 front-end processors, which gives you an idea about actually how much it was doing. And they ran that until 1992, June 1992. I know the exact date because I've just been reading a little account from somebody. I won't name them to spare their blushes, but I was in contact with them finally last night, and they wrote a little thing. They were one of the very first users of EMAS, and they were also one of the very last, as a postgrad in the first one, and then later on at the other end. So that was rather nice, I thought. I've done a brief timeline, just so this is to refer to afterwards more than anything else, but it gives you an idea where the various things happened. So EMAP was development only, and that went up to 1970. EMAS 1 went from overlapped that a bit, and then went up to 1979, and then the others on the 2900 and then the Amdahl and the NAS. Of course, the thing about the Amdahl and the NAS was that they were IBM style machines. They'd already got an IMP compiler. Didn't have to do a great deal to it because they'd used it on the System 4. The project spanned 26 years in total, and they had a user service running 22 years, which is pretty good for a system like that. The Kent service spanned 7 years, which is just on the 2900. It might have gone a lot further, but it didn't. But the development team was always very small, typically a maximum of about 10 people at any given time. And I did know most of them. They were really nice people. So that's really what we've got to. I seem to be running all right for time here, just about. So the next part of this is the history at the University of Kent, which is a bit more detailed because I know more about this. So a message just somebody's asked about, I might as well answer it now, a question about the paper. All the papers that I mentioned will be on the website. There's links on the website, so no more to be said. That might forestall some other questions. We have been running the Kent Online system COS on an Elliott 4130, which had 64 kilowords of memory, and then later on 96. We added a second one in 74, a second-hand one. And really all we got on that was basic for teaching with some editing and so on. And then for a batch service, we were running Algol and Fortran. And in 1976, we got an ICL 2960 running VMEK. We didn't want the 2960, we wanted the PDP-10. But the politics of the time was that you couldn't do that. The politics were very much buy British. I think that was the tail end of the Wilson government. It was unreliable. The combined hardware and software MTBF was about 20 hours, right? And I was talking to somebody, reading an old email from one of my colleagues, and he said he never realized it was that unreliable because he was busy using Unix. 200 bug reports in about a month. That was me. The reason was my job was to actually test practically everything because we had naive students using this. And I'm sure they had little effigy with pins stuck in it down at Bracknell, you know, because it was just, apparently I did have a bad reputation. It wasn't user-friendly. Many of you will be familiar with ICL editors from the early days. You can only go forwards in the file or perhaps backwards in a line. And we weren't used to that. We were used to something much better. And so we implemented a couple of editors. Some students wrote for a final year project, what they called ICE, an in-core editor. And we also implemented the Unix editor, ED, or a version of it. That was all right until 18 months later when ICL proposed to re-engineer VMEK. And they said they were going to remove some features to make it slimmer. Unfortunately, they were vital to us for running the workload. And we couldn't see how we could manage a system like that, which was a real problem. And so it was time for us to investigate alternatives. VMEK went on actually to be junked a few years later. And I've been in contact with somebody who worked on VMEK. He said he was quite relieved to find, given how rude I'd been, that he didn't start working on the project till after we changed over. But anyway, he said that it actually got it working quite nicely and it was pretty reliable. It was awful in the early days, but it was pretty reliable by the time they'd finished, and then it got junked because of the ICL politics. So we, again, were looking for alternatives. And we had this guy came down from Edinburgh called Peter Stevens. Peter Stevens installed EMAS in one evening, finishing in time for me to take him down the town for dinner. And it was really, well, the first thing I should say is my boss, the director, Brian Spratt, who many of you will know, a bluff Yorkshireman, he took me aside and said, can you sort out with Peter, you're the operating systems person. I hadn't even started teaching it by that point, but he suspected I was the hacker for all years before who'd subverted the entire operating system. And so he said, take him to dinner afterwards. He said, now, I'll warn you, he said, he doesn't suffer fools gladly, lad. And I suppose that's true, but I'm like that too. And actually, Peter was so nice. He was always nice. Even when I stayed with him and his wife for a while, he's a very, very nice person. I was really the only EMAS person there, systems person, at any given point, doing the actual system. But what Peter handed over to me were two big, thick volumes of implementation notes, working implementation notes for EMAS. and very detailed, and I still have them, and they're also accessible via the website, and they're really useful. This meant I spent a lot of time going to Edinburgh, and that was great. I made a lot of good friends. It was very morale boosting, being the only person at Kent supporting EMAS, and with the Unix people all saying, well, Unix is the future. It was all a bit demoralizing. You go to Edinburgh and you'll be like people, and it was great. And we had some really good trips out to the pub and to the restaurants as well, so that was good. And I feel I was a catalyst in some way, because I remember sitting in the coffee room at Edinburgh and hearing people talk about different parts of the system, and realizing that person over there didn't know what that person over there was doing. If you ever read Death World 2 by Harry Harrison, you'll know what I mean. I was able to say, well, actually, look, why don't you two together? Because you could do this. And they go, yeah. And then they go off and they'll be very happy. I remember one day mentioning to Peter Stevens, who was the person who wrote the original, or was responsible for the original editor, and I was talking about an algorithm I'd read the day before for spell checking, which I'd implemented back at Kent. And he took the algorithm from literally our conversation, went away, and by lunchtime, I think it was, he'd implemented the spell checker inside the editor. So that was really good. I also provided other things like line counting on printers and stuff like that. But I didn't do networking on it. That was somebody else doing that. We had a different network to Edinburgh. But early testing did give us some problems. We were running user trials, and the EMAS director, which I'll talk about later, we had a bug there which had never shown up at Edinburgh. I now realize that's because we were only just behind the front there, behind the leading edge. If you have a lot of users registered on the system, they all had to have an area on the disk for them. And when that went past a certain number, then these things had to be paged in and out. And there was a semaphore associated with this, and the semaphore got stuck. I went away and looked at the code, and I actually managed to work out what it was, because I spent hours reading the code. It was fascinating. And then I got this excited phone call from Edinburgh telling me the same thing. And we didn't want to shut the system down. So we fixed it by typing a command at the operator console to unlock the semaphore. The system's message-based, and you can fire messages anywhere to do anything. The procedure for doing this is called a PON, which apparently stands for parameters on queue. And these, you could type a PON at the command console, operator console. We call that a hairy PON, because that's exactly what it was. And it got to the point where somebody presented me with a small doll, a troll-like thing with a hair on it, and said, that's your hairy PON, and I kept it on my desk here afterwards. So yeah. Unfortunately, we found that the system was a lot slower than expected. Turned out to be this ranging compatibility again. There was a different place to turn on the translation look-aside buffers in the 2960 to any other machine in the range. And you had to tweak a different bit. So back to the operator console on the running system, writing the right value into the image store, and it worked. We obviously fixed the code as well. The other problem we had was a hardware one. We had parity errors on the link between the PDP-11 front end and the actual system. And that was turned out to be an earthing problem. I can't remember whether we took an earth connection away or put one in. The reason was they were on different power feeds. There's a power feed at one end of the room which had the 4130 on it. We now got all the deck equipment on. The other end was the 2900, which was on a motor alternator. So we fixed that pretty quickly once we knew what it was, but it took a couple of months to work it out. Our network was entirely a Cambridge ring, and the differences were all inside the front end, so we didn't worry about that. As I said, we were running user trials, and the changeover took place after the end of term in December 79. No going back, because we just couldn't try and operate with files on two different systems. One of my colleagues wrote a program which literally read the VMEK disks and transferred the files inside them to EMAS, which was very clever. And the MTBF went from 20 hours to about 2,000 hours. Now, one of the reasons was obviously the software was more reliable, but the other reason was that the software was tolerant to hardware faults. I'll give just a couple of examples here. One was that the disk controller would lock up for no apparent reason. And if that happened with VMEK, it'd say, oh, it's not responding, I better crash, you see. EMAS said, let's try and switch it into diagnostic mode. Yeah, okay, right now we can reload the microcode, which came off compact cassette and took 1.5 minutes. But for 1.5 minutes, it would cue all the disk rests and then carry on running. Users just got a pause of 1.5 minutes, so they got used to that. Didn't happen all that often. The ICL engineers were pretty distrustful of us, particularly one guy who was actually very much a company man, and he in fact was a former student. He was an electronics student from Kent. And the other problem we had there was that it's got Hamming correction on the memory. So you can get a single chip, a single bit fault can be corrected automatically. 2-bit fault can be detected, but you can't correct it. So when VMEK got a single bit error, what it did, got the interrupt for it, it read the memory location out, wrote it back to clear the error and carried on running, which is all very well, but eventually it degenerated into a 2-bit fault. So what EMAS did instead was it logged it. And there was a program that ran once a day called the journal system, which analyzed the logs and printed out details of which board was failing and which chip on the board was failing. And then we gave that to the engineers, and they were very, very happy. So yes. So the engineers really came round to us in the end. We had a serious problem in 1982, a microcode crash. This was quite interesting. The system was just stopped dead for no apparent reason. And EMAS wasn't crashing. We went to look at the engineers panel and the microcode had halted, which is not what it's supposed to happen. It turned out it was a hardware design error. The microcode was handing off decoding a descriptor type, which is just a number, to a piece of hardware. And the hardware was supposed to validate that for good numbers and bad numbers. The number was then passed back, if it was good, to the microcode, and the microcode would use a jump table on it. Unfortunately, the hardware was failing to detect one particular number. So it came back to the microcode used the jump table, and it went straight to this can never happen, halt. And that was a problem, obviously. I fixed that by teaching myself a bit of microcode and hand assembling some 60-bit wide microcode and putting it into a patch area. And that generated a new error, a new hardware error, a subtype, and then we modified the whole system all the way up to handle that error. It was a physics postgrad, of course, it usually is. And the physics postgrads was running his program, and it would crash, and he'd go away, and they'd do it again, and they'd do it again. And then he never realized there was a causal connection, but he got fed up. And a week later, he'd come back and run it again a few times. So we get spates of crashes. So yeah, that was a bit of a problem. Other than that, it was pretty good. It did help that I had the circuit diagrams, and I had the source of the microcode, and I had a fiche reader and a microcode training manual. We had a very cooperative site engineer called Harry Sweet, who was a lovely man, and in fact, I later taught his grandson computer science. Right, so we then managed to get a second OCP, which is the CPU in most systems. We got that from government sources. It was the 1981 census. We had to go and look at it in Southall and bring it back, and we got some more memory too. And it worked straight away, except that cross-reporting between the two OCPs didn't work correctly. Guess what? Range incompatibility again. And we asked ICL for documentation on this, and we never got it. So eventually, I went and sat down with the microcode for another couple of days and reverse engineered the microcode to work out what was actually supposed to happen and which bits you were supposed to poke. And we got it working, and it worked for the next 3 years, with no trouble at all. And by that time, I'd learned a great deal about the 2900, and I could probably give an entire lecture on the 2900 alone. I do know it pretty well inside out now, certainly at the software level, but all the way down the software level. The contributions from Kent during all this to EMAS, well, we did various system enhancements. The printer accounting was one. We had somebody said to us that we must have a way of counting how many lines, how many pages people have printed, so we can, if necessary, we can enforce it. So I spent some time inserting that in at the very lowest level in a very efficient way. And it printed out the numbers at the bottom of the page. Nobody ever looked at it, except possibly the users who were scared by it. So it probably had some effect. But we had a basic system. The basic was actually from the BMEK, but We put shims around it to make it work on EMAS. We had an assembler, which we'll come back to, but basically it was the ICL assembler for VMEK, again with the shims. I wrote a BCPL compiler, and we had quite a few packages, and we did another editor. So there was a lot of stuff there. Okay, that's our TWIC 960 circa 1981. There's not a lot to say except that the OCP is at the back there on the left, and the black bit on the left-hand end is the engineer's control processor. To the right and behind the mag tapes is the store access controller and the disk controller. In front of that, you have a general peripheral controller just by that rack of disks. The operator console with 2 screens, which was pretty normal. Reconfiguration console to the right, and the black thing right over on the right, I don't know why it's black, but it is actually the 1134 front end. It got a lot more crowded when the second OCP went in. Right, so that's the second part, which is the history, but now I think possibly the most interesting part is the implementation. The implementation is quite difficult to do if you want to cover all of it, so I'm just stuck to the 2900. The 475 one was a moving target, and I've never seen any sources for it except those that have been inherited and turned into EMAS 2. The IBM one, I've got some of the sources, but they were from the time I worked on the 4381, nothing much later. The sources for the 2900 are almost complete. There's only 2 tiny missing bits from the system. The information I've got here is taken from papers and manuals, but mainly from reading the source code. Over the years, I think I read almost every line of the source code of the bootstrap, the supervisor, the director, subsystem, and a lot of other stuff, all the system processes. So I do know it pretty well. Before I go on to the main part of the system, I want to talk about how it handles files. Some of you will know this, but files are not accessed in the conventional way. If anyone knows about multics, it's like multics. You connect a file into the virtual memory of a process, and then the user sees them as a piece of virtual memory. You don't actually ever read a file in. So connection itself is a bookkeeping operation. No real I/O takes place apart from just getting the directory and so you can find out where it is. Files are divided into pages of fixed size, and guess what? They're the same size as the pages that the memory management uses. And a page of a file only comes in if it gets referenced. It can be referenced as data, but it could be referenced as code as well, because the way you load a program is essentially by connecting its executable file in virtual memory. And then you jump to it and it gets paged in, but only the bits you're using. So that's nice and clean and simple. When you change a page, if it's a file that can be changed, it gets written back to disk, either when the memory is needed for something else or because you've disconnected the file. So that's the only primitives you really have. I'll talk about file primitives a bit in a minute. And you can share files between processes. So if 2 processes are accessing the same file and the same page of that file, only 1 copy will be in memory. So you're saving memory there so you're sharing what would be I/O buffers, if you like, which is quite good, I think. It's also, of course, the case that you share code. The code of a program is connected in 2 different virtual memories, but using the same page. So the code gets shared automatically. Now, this diagram is historic. It's over 50 years old. I had to include this diagram. I finally managed to get a copy. It took a lot of negotiation and so on to get it out of the university library. But that diagram sort of indicates how the mapping works, sort of. It doesn't tell you a great deal more, but I just had to do it. I had to improve the size of the wording because it was very small. Right, so I'm now going to start on the system itself and just work my way up from the kernel. The kernel is a message passing kernel. Everything's done by passing messages around. And the messages are always the same size, 32 bytes, allocated from an expandable pool. It's in system virtual memory. 4-byte source number, 4-byte destination number, 24-byte payload. Why that size? It dates back to the system 4. They wanted to pass a message between contexts without having to do a lot of fiddling with memory. So they passed it in the floating point registers. And the size of the floating point registers comes to 32 bytes. So that's why. I thought that's something I didn't know till recently. And you've got various non-page system processes, which are effectively bound in with the kernel. And I'm not going to go into detail, but device drivers fairly obviously. The paging manager, which actually moves pages around, but nothing more than that. Implementation of semaphores, something called the active memory handler, which you'll have to go and read the papers to find more about. The scheduler, the handlers for the interval time and real-time clock in the hardware. Configuration control, because you can configure things in and out on the fly. If you're running a dual system, for example, you can configure out some memory, you can configure out a CPU, you can configure out a disk and a controller, and you can configure them into another system and boot that separately, and then bring them all back in again afterwards. So you do development without stopping the service completely. And something called the bulk storage mover, or just the bulk mover, which moves information to and from disk to tape very efficiently. And collectively, this whole thing, which is the kernel plus the processes, is known as the global controller. And there's one instance of the global controller for every CPU, every OCP that you have. That's really all it does. It's not incredibly small because of all the device drivers and everything else, but the actual part of it that does the message passing is really quite small. I was shocked at how small it was when I actually measured it. Now, this is where it gets interesting, and I've got a diagram at the end of this because one has to say it in words, but then there's a quick diagram to explain it as well. Every non-resident process, so we're talking about user processes, privileged system processes, and so on, every one of those includes an instance of something called the local controller. And the local controller is resident, it's actually bound in again with beside the global controller. And there's only one copy of it, it's got shared code, and it's privileged, very privileged. Every process uses the local controller, but has its own local controller instance data and stack. In fact, they're the same thing. And the privileged but page portion of each non-resident process goes above that. So the resident code for a process is the local controller. The non-resident is part of something called the director. That shares code across all processes. And again, every process has its own data and stack. It's become clearer when I do the diagram. The non-privileged part of each process can be anything you like, absolutely anything you like. It's supplied by something called a base file. Why do we call it a base file? It's connected in virtual memory and becomes whatever you want to do at that level. You can make up your own base file and connect it in virtual memory and use it. And that's all paged. So most of the system is paged, and that's important. And the standard base file is the Edinburgh subsystem, which they wrote, and that provides the user interface and a lot of support stuff, such as library routines and so on. But if you want to do your own version of a base file, you can. You know, that's fine. And other base files exist. It's that scientific jobber again. That's a base file which will run fast batch, and particularly for student work. And then we've got other processes. We've got page system processes which are privileged in some way, and there are 5 of those. It started off at 3 when I started using EMAS, and it grew to 5. They're all normally automatically started. There's direct, which is operator control. It runs the operator console. It handles all logon requests and starting processes and some other functions. Volumes, which is a tape administrator. It tells you when to mount tapes and when to unload them and so on. But more importantly, it handles the backup system and the archive system, which I'll come back to. There's a spooler, which does exactly what you'd think, except that it does it for remote devices as well. So it'll send stuff out over the network, as well as just the local printer and so on. FTrans, which is a reasonable name, I suppose. How many people remember the colored book protocols? Yes, right, okay. Well, Blue Book protocol was file transfer, and so FTrans did that in its entirety. And then we got Grey Book, which was the mail protocols. So we had electronic mail. We had mail from quite an early time. And they all run as paged user processes, but they're privileged. They've got a higher level of privilege. And they have a specialized base file for each one. Apart from direct, which is weird because it has no base file. So What this means is that, we now got onto the local controller. The local controller is, as I said, a resident part of each page processes. And this is where it all really happens, the really clever bits. Among other things, it handles paging strategy. The paging mechanism is, of course, back in the global controller. That moves pages around. The local controller decides at which pages to move, but it's per process, exactly that. Every process gets given a page quota by the global controller, and it's not allowed to use any more pages than that. And the local controller, being privileged, enforces that. The quota will change over time according to how the process behaves. If it needs more pages constantly, then the local controller will ask for more, and then it will start to, it'll be given some. So if you get any thrashing, excessive paging, it's local to that one process because it can't use any more than that number of pages in memory. If it needs more, then it will get rescheduled and it will get a different CPU profile. Normally it'd be given more CPU time, but it'd be given it less frequently so that it doesn't affect the system too much. And essentially it gives the process a more bumpy ride, if you like. And the whole algorithm for that is table driven. You can change it if you want to. We never did. And batch processes have an interleave table. It's actually effectively a separate table. And there's more emphasis there on long time slices and less on response time. They're given and they're put on different kinds of CPU queues. So that way, the idea is that the paging behavior of a process and its CPU behavior is only going to affect that process and not the others. And each process is therefore responsible for all of its page replacement. So the policy is done, the strategy, if you like, is done with local controller. Global controller just does what it's told. Now, there's one slight problem with that, and that is the quota system ignores page sharing. If you give every process a quota of pages, but some of those pages get shared between processes, then you're wasting space because some of the page space isn't going to be used. What do you do about that? What they did was they decided, and this didn't happen to start with, and I remember being there when they were doing this, they overcommitted the memory. They said, well, okay, the global controller says, I've got X pages to allocate to all the local controllers. It actually allocates a few more than that because it knows that some of them will be shared. And that should work in theory. But of course, sometimes it's going to go too far and there'll be a deadlock. There'll be two processes that can't proceed because both of them want more pages. And that's detectable. And what the system did was just chuck one process out, just chuck all its pages out and start again. But that would only happen, you hope, about every 10 minutes or so it was acceptable. And they decided to make this dynamic. So the overcommitment ratio was set and the system would start to run. And as it ran, they'd see, did it take 10 minutes to a deadlock? It took longer than that, we could overcommit a bit more. It took less time, we should undercommit a bit, and so on. That was the idea. First time they tried it out, they went home for the night, came back the next morning, and the system had said, "Woo, there's practically nothing happening," and the overcommit had gone right. And that meant that, of course, the system was going like a slug and tune itself back down again, which took a while. So they had to put a limit on that. But it did work, and it was fine. And made it much more efficient in terms of space. So sitting above the local controller is the director. The director is entirely paged, and it's part of every process. As I said, it's got its own data, it's got its own stack, and it's implements the file system. The file system is paged. It implements system calls in the 2900 hardware sense, call descriptors, and it passes the local controller details of what needs to be done via another hardware call. It handles exceptions, what on the 2900 are often called contingencies, and it handles functions which are local to the direct process. The reason why the direct process has everything built in is because you have to have a process that can always run, regardless of whether it can find a base file. There might be no file system, so direct has to have that built in. And that's essentially where your security border is. Nothing can get past the direct system call interface unless it's been validated by the director. So it's less privileged than the local controller, but it's more privileged than the user process. So that's how it works. The direct process is unique. It's got no base file, or it's all inside the director. It does operator, I think I said all this already, but operator interactions, user logons and everything else. So direct has to be running for anything to work. If direct dies, it's curtains, basically. Now, just to give you an idea of what the file system primitives are, and there aren't very many, there's connect and disconnect for virtual memory. You call connect on the file name and it gives you back a virtual address where you can find the file. Disconnect does the opposite. Create creates a new file, but it's empty of whatever size you want. Destroy, obviously, that. Rename, obviously. Permit changes of permissions for a file. And that can be quite fine-grained. You can say, only allow this person to access, this user to access a file, only allow people whose usernames have this pattern in them. Or you can even do, and it was done, saying, let everyone access this file apart from that one person over there I don't like, right? And that will work. So as a call to get a list of all the file names in your directory. A couple of interesting ones are the offer one. Offer offers a file to another user. This is a way of letting people share files without actually changing permissions on them. So when you offer a file to another user, you say offer file name, username, and at that point the file is locked and you can't access it yourself unless you unoffer it. The other user can do an accept, and that will transfer the file to their ownership and remove it from yours. We didn't realize quite how this worked at first, and we were offering files expecting them to, when they accepted them, to just take a copy when the file had gone. But we got used to that. The last one is NewGen, which is nice. It gives you the opportunity to change a file while it's in use. You can have another file, which is to overwrite the file that's in use. It will automatically do that for new users of the file, and obviously existing users carry on using the file as it was. So that's quite a nice feature. We use that a lot. Above the directory is a subsystem, and the subsystem is the user part, as I said, the base file. And the Edinburgh subsystem was really all that anyone used. It runs in completely untrusted mode. Mostly you'd be accessing it via an interactive terminal, but batch programs effectively did run in it. And later on they developed a sophisticated batch control language so you could actually make decisions inside a batch file. But the subsystem, as the rest of it, is a single process model. When you type a command, it doesn't start a new process like it does in Unix. It just carries on running in that process. The worst that can happen is that you overwrite something in the subsystem and it crashes, but it just locks you out. No, it's not a problem. And you can install additional commands from public files, and you can say, file over there, give me all the commands in that file, and it'll add that set in for your use. Or you can write your own, and usually they're written in IMP, but you can write commands in Fortran or Algol or whatever. And the commands in the subsystem, I'm not going to worry about the ones at the bottom there because they're pretty well what the director does. You've got analyze, which tells you about a file, and it will do that in a type-specific fashion. So it'll tell you, in the case of an object file, it'll tell you, what the structure of the object file is. Alias, because people obviously wanted to turn destroy into RM. Archive, which queues a file for archiving and removal from disk. But we only ran the archive once a week, and at that point, 2 copies will be taken on different tapes, and they'll be and it will be removed from disk. More about that in a minute. Obey just runs a command script. Files gets you a list of files. Edit, well, actually there were several editors, and you could use whichever one you wanted. One of the editors, called ECI, which some people may know, the Edinburgh Compatible Context Editor, has been re-implemented countless times, and you can get it on practically any system you can imagine. There's a C version, I think there's a version in Fortran, there's all sorts of things. There's a copy command, which just says copy. Much better than VMEK, where copying a file involved typing 3 long commands, until I wrote a copy program. There's an option command. You can change the way your command interpreter works. You can change all sorts of things. Really interesting thing is the cherish command. Cherish is to mark a file you really care about, right? And you just sets a flag on the file, and that means the file will be backed up. If the file isn't cherished, it won't be backed up. And this is very good because an awful lot of users just create files willy-nilly and they just overload the whole system in terms of backup. They don't really know what they're doing, or they're only occasional users. And so cherishing the file was the way to say that. Of course, occasionally people didn't cherish a file and then said, I need it back off backup, and we said, tough. We would actually make it very clear to users, it was part of the initial introduction that this would happen. If you don't use a cherished file for 4 weeks, it gets transferred to the archive and removed from disk. If it's not cherished, it gets deleted. And there's no backup copy, remember. All right, so that also taught people. They always had to learn it once. Yes, but there, that's... So, this is a very, very small set of commands. On the website is a complete user information card with a load of commands on it. Now, going back to files again, I was saying that files are just arrays of bytes. Oh, one other thing about the commands, by the way, yes. Just before we went live, the month before, I got married. And I got a telegram from the EMAS team. And the telegram was almost entirely constructed from EMAS commands. So it's just something like cherish and obey Tina forever. Sad here you're abandoning your Scottish imp, and so on. I can't find the telegram. It's not in our wedding album. It's very annoying. So yes, files are just arrays of bytes. That's how you access a file. The subsystem suggests that you should have a minimal amount of information. Unix diehards will always tell you that Unix files are just a stream of bytes, apart from the ones that have magic numbers on the front, and apart from the ones that have some sort of internal structure. So EMAS just has the first 32 bytes, and it says things like what the file type is, text, object, whatever. Perhaps it's got a record structure. Tells you the physical size of the file and the logical size, how much of the last block is used. And you can have basic partition files, which are similar to the IBM type things, but a bit more flexible. You can copy files freely into and out of partition files. You can't normally write into them unless you write a special bit in your program, but you can read from at any point. So you get a chance to do that. And later on in the life of EMAS, about 1983, 84, I think, they decided to have a thing where you could have subdirectories. We hadn't got to that point. Bear in mind the age of the system. It's not entirely surprising, but there we are. So what I've now got is a diagram of the system structure, and I just wanted to, this is really to sort of explicate what I talked about. The global controller sits at the bottom, and that's device drivers and stuff like that, non-page processes. And on top of that, you have the local controller, and the local controller's got data and code. And in between the two, as you can see, everything below that line is non-paged. It's part of the bound-in system. The paged part is the data for the local controller. And that can be paged out. So even that part of the system is paged if it's inactive. And together, that part of the system is known as a supervisor. And I apologize to any EMAS team people, particularly Peter Stevens, if he's watching, in case I've got that slightly, I'm glossing it a bit. So above that, you have the director, of course. Ignore the bit on the left-hand end. And the director is, there's a director for each process, and that's all it is. And that's paged again. And above that, you have the process itself, which would be the base file, the subsystem, or whatever it happens to be. And on the left, what I put is actually system page processes. So that would be probably volumes at process 2, for example. And then user processes on the right, which are they're all paged. And direct is special in that it doesn't have a base file, as you can see. It doesn't have a base file, as I said before, because if it did have one, there'd be a bit of a problem if you wanted to do something without a file system. Lastly, communications controller, special version of the local controller with its own page allocation. No director, no base file, and it does the I/O to the communications system, which includes local devices such as printers and card readers and everything else, and also to the network. All I/O is from chunks of files that get paged in by the local controller. The terminal buffers are just files, and there's a circular buffer in each of those, and they get mapped into the memory of the user process and then mapped into the local controller, a communications controller. Last thing, initial program load, IPL or boot. It's large because it actually has to establish the configuration of the system, and it interrogates that and times it out and so on. called GROPE, which I think may be an IBM term, but it stands for General Reconnaissance of Peripherals Equipment. Essentially, it's a chopped-down version of the global controller, and they called it CHOP-SUPI, chopped-down supervisor. CHOP-SUPI gets loaded by the hardware. Initial register settings come with it, and it runs. The OCPs are queried for their types and their subtypes. The SMACs, which are the memory controllers, are queried for what memory is there, and there may be gaps in it. The SACs, the store access controllers, are queried for the trunks, which are the controllers. The controllers are queried for the streams, which are the devices, and so it works it all out and builds its tables. And CHOP-SUPI contains commands for disk formatting, for system transfer from tape, and then loading the actual system. So the way you install EMAS is you boot it off tape, you format a disk, you transfer the system down onto the disk, and off you go, reboot. And that is nearly that. However, there is one last bit. This is the Computer Conservation Society. So, just one more thing. Resurrection. I tried to look at what would be needed if we wanted to run EMAS again. We've got the source code, there are no binaries. The way we carried them over via VAX VMS meant that we only carried across just things that were a source. The EMAS original source is probably gone. We've got the source of EMAS 2900, apart from a couple of tiny bits, which are the assembler and the tape boot block. But I have a hex dump of the tape boot block, so that could be deconstructed if necessary. EMAS 3, I've got bits of it. So if you wanted to resurrect EMAS, it would have to be on EMAS 2900. Nothing else would work. But the source code is the easy part because we have it. Next you need is an assembler, because that bootstrap, it's not very big. It's about 600 lines, 650 lines, and the tape boot block need to be assembled. No source is available. We could do it by hand, but it would be not a good idea. We can't use the ICL assembler because that was a binary, so we're stuck there. However, I have written and tested an assembler. It's 4,000 lines of C. I do tend to write quite a lot of comments, so don't worry too much. So we could assemble stuff. 2900 assembler works. We need an IMP compiler, and this is really tricky because it has to compile imbated dialect, and which is different to some of the others, into 2900 code. And it doesn't really matter whether it's for which sort of 2900 it's for, it's still the same. I've got the source, but you can't cross-compile it with other IMP compilers. It's got too many weird things in it. One is that the 2900 is a big endian machine, and all the modern systems you might be running an IMP compiler on a little endian, and the source just doesn't work. It also uses the IBM HFP, the hex floating point format, because that's what the 2900 used. I think they changed their minds about that, and then they decided to do that. You'd also require the ancillary modules the compiler uses, which are inside the subsystem. So you've got the object code output, which builds an object file, and the compiler environment, which provides things like work files and so on. I have written and tested an IMP compiler, 27,000 lines of C, and it works. And it's pretty well, as far as I can tell. I've done quite a lot of testing on it. It's not perfect. I currently know of one bug in it, which I have to fix. And I was going to do that, but then I couldn't because I had to write a pesky lecture for the CCS. All right? So that's where I am at the moment with that. Need a linker to link the object modules together. CHOP-SUPI is about 8 modules. And we've got the source code, but it's in IMP80. It requires library routines and the compiler environment again. It's a bit of a problem. And it's got very heavy dependence on the virtual memory concept of EMAS and how it handles files. It randomly writes into files big chunks of code and moves them around. So you'd have to rewrite it completely. I have. 1,000 lines of C, not too bad. And it works. You need the utility programs. Particularly, you need ones that will take a linked file and turn it into a binary image, an image you can load into memory or whatever. And EMAS has got about 6 different ones. Most important to start with is CHOP-SUPI. But to build CHOP-SUPI, you've also got to build things like segment tables, because when the system starts up, it's running in virtual mode. So you need it straight away. And the supervisor's got similar problems. The supervisor is the kernel and the local controller. So I've written some of those, and I could actually build a CHOP-SUPI. Lastly, hardware. I could either go cap in hand to Darwin, and say, can we run it on that? But you know, it's a long way to Bletchley Park, so really a simulator is the only practical path. And there were two types of 2900 supported by EMAS, the P series and the S series. I'm only going to look at the P series. I don't. At the time I started looking at this, I didn't know very much about S series. I know more now. And these are the components that are required, which are listed there. Probably the most interesting part there is that, well, no, I'll come back to that. It's all right. Yeah, I'll come back to that. So I'm not going to go through those in detail. But the P series structure is this. You have the store multiple access controller, which contains the memory. And it's got ports on it, usually 4. One of those has the OCP on it, and you could plug a second OCP there on the left of that. And it has a store access controller, which is an I/O controller, which goes also, and you have 2 of those if you want. The SAC has in it a file peripheral controller, which runs disks, and obviously you've got the disks down the bottom there. And the SAC has practically everything else in it as well, on something called a general peripheral controller. And the general peripheral controller will give you the operator console, it will give you the printer, it will give you the tapes, give you the front end processor, and 1 or 2 other things as well, like card readers, and punches, and so on. So I put this on because when the slides are inspected by somebody, they'll actually get an annotation of what's there. A simulator is in progress. 35,000 lines of C so far, and I haven't finished. So far, I've got the OCP with all 128 instructions, interrupt control. It does segmentation and paging and supports virtual memory. It's got a clock. It supports just the P series machines, the 60, the 70, the 80, 72 and 76, and so on. And only 1 OCP. It's got a simulation of a simple engineers panel to give some diagnostic information. It's got a SMAC, in fact, up to 8 SMACs, which give you memory up to 32 meg. But only on a 2980. If you're on a 2960, you can only have 2. It's got a SAC with auto configuration, so you can ask the SAC what controllers it's got. I've got a GPC which supports auto configuration, so you can say what have you got attached to your streams. Got an operator console with keyboard and 2 screens. Haven't tested that very much so far. The 2 screens are done by using a VT100 style terminal and addressing it dynamically. It simulates a printer for an early diagnostic output, because when the EMAS loads, it starts spewing stuff out on the printer, saying what it's found and all the rest of it, for historical reasons. I haven't done tape drives. I haven't done the file controller. The disk drives are fairly easy because they're actually IBM 3330s, -1 and -11, and diagnostic information on that's easily available. I haven't done a card reader and punch, but they're fairly easy. And I haven't done the front-end processor, which would be a bit tricky. If you wanted to do that, of course, you then have to resurrect the system that runs on the PDP-11 as well. What works? TROPSOP loads and runs up to a point. It actually asks the OCP what it is, finds out its subtype, does all the necessary checking. It then asks the SMAC, how many SMACs are there? Is there any memory there? Is the memory in contiguous blocks or not? SMAC will tell you all that. And it then asks the SAC what's attached to it. And it asks both SACs, in fact, that might be attached. And it will correctly handle the timeout of the one that the simulator will time out the SAC that isn't there. And that works. The SAC will correctly, it can then be used to interrogate the GPC, and the GPC could be used to interrogate what's attached to each of its streams, and that works. So it's discovered all the stuff that's in the system correctly. Next thing it does is it clears the memory, and that's where it stopped, because I've got an error there where, because of the endian business, I seem to reverse the two halves of a constant.
Both of which are 0.
No, they're not. No, this is the descriptor for accessing the memory, you see. That's the problem. So that bit doesn't work. But that's where I was when I started on the lecture. So as you can see, it's going a long way. If you look at the moment, nothing comes out in the operator console, because at that point, the operator console hasn't correctly been initialized, because we've only just found out about it, right? So what happens instead is that the system queues those, they're all in messages. If you look at the message pool, you can see all the messages coming out saying, I have found this, it's this type of OCP, and all the rest of it. So we know it's there, we know it's worked, and the code has shown me that. So it's actually working. and I would expect to get Chops to be working probably by about the end of January, the way things are going. One of the problems is that while I've been working on this, I haven't done much else. And I'll tell you how long it's taken in a minute. But one of the things is that all my Unix systems at home are in dire need of an upgrade. So that takes about 2 weeks to do them all, because there are, I think, 10 of them. All right. So it's going to take a while to do. And I will be starting that tomorrow. So yes, there'll be a temporary. How was it done? Well, I have plenty of time. Let me explain what happened here. Back in 1989, I thought, wouldn't it be nice to have an IMP compiler on the PC? So I started writing one in C. And I got to the point where I'd finished a syntax analyzer, which worked on small programs, but not on large ones. And then I didn't have any more time because I got a new post in the university. So I didn't come back to it really until last year. In fact, no, it wasn't. It was about January this year, actually, January or February. And all I had was a syntax analyzer that didn't work. I managed to fix that bit fairly quickly, but the rest of the compiler took a long time. The original IMP source has some comments, but not enough. And nearly all the variables are very short names, and they're duplicated in lots of places in order to cut down on dictionary space. So it's really hard to actually, and it's structured in a very strange way to improve its paging performance. So it's really, really difficult to do. But I got there in the end. It was actually, I started this year, in fact. I started the simulator back in 2002, and I got totally discouraged because I had no hardware documentation and I couldn't get any. Right? It's really hard to get documentation on P-series machines. I did hear that you can go down to the Science Museum, but it seemed to be very, very limited access, and so I didn't go any further with that. So I had no documentation, so I just got discouraged and stopped. I mean, I think I asked somebody here about 8 or 9 years ago. So, lack of documentation. Just 2 partial documents of the order code. That's pretty well all I've got. I couldn't source document anything else. How did I develop the simulator if I didn't have any hardware documentation on? I reverse engineered the source code of EMAS. So that's why I know the source code so well, because I've read every line of Chop Supi and pretty well every line of the supervisor in order to get all the device drivers and how they work. So work continues. And that really is the end, apart from a bit of admin. First of all, help. If anyone knows how I can get hold of those hardware documents, it'd still make life a lot easier. And it would mean I could probably run VME on it as well if whenever wanted to. I've got some S-series documentation. I didn't choose S-series because when I started this, I knew nothing about S-series and I had no documentation at all. I do now. I had quite a bit, so I would do that in the end. There's no reason why EMAS can't run on S-series. The source code supports both, but I'm building it for P-series. And are there any other copies around? Perhaps people at Edinburgh know, I don't know. So, conclusion, EMAS was a relatively long-lived system, 22 years. Very reliable, it's efficient. The university environment is challenging, certainly, but it's not the workload model that you have for everything else. EMAS would not necessarily work in business. It was relatively portable, as we saw, lots of different varieties of system, but not widely used. But I hope to have it running one day fairly soon, perhaps. So, last slide is contact details. You can contact me at that email address. I've got an EMAS website, which is live right now, and you can go to it. It's got the references there. There are too many references and acknowledgements to include on slides, and there's too much I wanted to say. And there are links in there. Anyone who was asking about documentation and everything else earlier on, and those papers and so on, they're all linked. The common ones are linked via that website. But absolutely everything I have, including all the source code, is on my other website, ancientgeek.org.uk/EMAS. So you can go and find it there. So that's it. I'm sorry I've run a bit longer than I expected, about 10 minutes longer, but I hope it was worth it. Thank you.
Bob, that was excellent. Thank you for that. I hope there are some, well, I should be astonished if there aren't. Questions? Dick, away you go.
Bob, on your BCPL compiler, it did eventually find its way out into the wild and it ran under VMEB. It was adopted by an accounting firm whose name I fortunately can't remember, and used in a package called Millennium.
Oh, I know. I did the work.
Ah,
I did the work. I sold them that compiler.
towards the end of my time in ICL, I was called in as a consultant, being the only person in the whole of ICL who knew anything about BCPL. It turned out that Millennium was not Y2K compliant.
Oh, dear. I know Millennium died eventually, but they paid me quite a lot of money, and it paid for my first IBM PS2, a big one. So I was not too unhappy. And I did Millennium on 2 systems, 2900, and then again on the VAX. So yes, but that was me.
Probably unsurprised to hear I've got some questions
yeah.
for you, Bob. Well, first of all, on the question of hardware documentation, I'll talk to you after the lecture.
Okay.
I think we can probably help with that. Just in general, talking about the EMAS system, and you mentioned documentation as well. It seems that when it was originally implemented, ICL must have been cooperative with Edinburgh at least, because there's no way otherwise they would have been able to write a system at that level.
They were sort of cooperative, and it wasn't. I mean, I think this happened. This is illustrated, I think, by the second OCP at Kent. The second OCP, when we wanted the documentation to sort out how to do things, we never got the information back from ICL, and we never quite knew whether it was because they didn't want to cooperate or because they couldn't find the right person. And I suspect the latter. And I think that's what happened with Edinburgh, because they got some of the stuff they wanted, but a lot of it was done with trial and error. If you read the source code, there are comments in there that says, I don't know why you have to do this, but you do. Yeah. So yeah, there was some cooperation, certainly. And they must have had that document at some point, but there's been no trace of it in Edinburgh that I can find. And I have asked all the right people that I know.
Yeah, I mean, on the face of it, it's an incredible achievement that they managed to do that with such a small team.
Yeah.
Do you have any sort of insight into how ICL managed to make VME so slow and unusable when a relatively small university team could come along and write something much more effective to run on the same hardware?
I think I covered that just now in a way. I mean, I think the workload for a university is very specific, and the university workload was limited in what they had to do, whereas VME had to pretty well do everything. Having said that, I think they could probably have done better. I thought it was very interesting that VMEK, for example, was pretty awful to start with. They got it into a pretty nicely usable state, but it took them 5 years, 6 years, and then they junked it. But talking to this person, as I said, I've recently come into contact with, and he was telling me that it was a shame because it was working, and I think they did get a lot better with VME. VME got considerably better after about 18 months when they produced a new release, and I think it improved again over time, but it was taking too long. They couldn't wait.
I mean, this is mainly to make myself known to you. My name is John Davis. I worked as part of the front end team in the 70s at Edinburgh. And most of what we did was latterly at least, was on a CTL Modular 1, which we used as a front end.
Yeah.
And we also used them as node switches in something called RCONet, which connected Edinburgh.
Yeah, Regional Computer Organisation. Yeah, I remember that. Yes. Yeah. But the Modular 1, I thought, was a front end really to remote job entry and things like that more than anything else. Was that right?
Yes.
Yes. Whereas the front end I'm talking about was actually the front end that ran connected directly to the RCONet.
Yeah.
Yeah.
Well, yours actually connected, as I recall. I mean, this is ancient memory now. To what were hardware multiplexers in effect. Whereas we ran a packet switch system that carried batch traffic. So we were running packet switching, way back in the early 70s.
I know. Yeah. Yes.
But it was only carrying batch traffic. Yeah, that's true. Yeah. So I had a whole lot of questions, but I could detain the meeting for.
Well, you can detain me afterwards. That's fine.
Okay.
So that's right. I'm here for as long as.
I think that's about it. All I want to say right now. But I mean.
Yeah.
I'll talk to you
Yeah.
on later.
Yeah, so what we did for multiplexers was we started off by, we had already written for VMEK, we wrote a PDP-11 terminal concentrator, which we called Yarrow, which was yet another rewrite of everything. I did the message push. No, what did I do? I did the command interpreter and everything else, and the paper tape handler and so on for Yarrow. And that ran the PDP-1103, and that supported a 16-port multiplexer or two, I don't remember. And we just carried on using those, and we put more and more of those in. And then it was written in BCPL. I did the compiler for that, or a part of it, and then we re-implemented it on a Z80. And the Z80 compiler came from Cambridge, and I did a lot of tweaking to it to make it do bit operations very effectively, very efficiently and tinily. And we ran the Z80 multiplexers for years, or terminal concentrators for years. So yeah, we also, of course, had to change the network interface because we weren't using the RCO network packet switching. We were using a Cambridge ring, and latterly several Cambridge rings. So the front end hid all that from the rest of the system. So you didn't have to change a line in EMAS to handle a Cambridge ring.
This is Nick Shellness. Hi. I've realized today that
Hello, Nick. Yes.
that global controllers and local controllers were mine. And we're done because we wanted to be able to drive huge numbers of printers and card readers, etc.,
Yes.
very efficiently. And using the normal user space controller would have been idiotic. So we split it to have stuff that was common to everything, and then stuff that was specific to a particular type of process.
I recognise the name. I've read all of your papers, I think, on the subject. So yeah, I've obviously had to simplify things today to get it all into the time. But yeah, great work anyway. Yes. And
The other thing that I might say is he couldn't join us because he's on the West Coast and it's too early. Little Bill Lane, who worked on global and local controllers with me, ended up running all of Microsoft Server and cloud development. So
he also did quite a lot. He did the the SMP stuff for Max VMS as well.
Yes, he did.
Yeah. Yes. so yeah. I see George Ross is there. All these names, actually, I'm quite interested to see. These names I've probably heard of, but not seen Colin. I haven't seen Colin Adams for ages. Yeah, this is wonderful, actually. Yes, I'm glad that so many people have managed to find out about this. All these names from the past.
If anybody has, remote has any quick comments or question they'd like to make, please do unmute and ask your question.
How about, this is David Huldworth from ex-Leeds.
You're very faint, David.
Sorry. How about demonstrating the portability by implementing EMAS on a more modern piece of equipment, like for instance a Raspberry Pi, which probably is about the equivalent hardware capability. And of course it does have the option, as it's an ARM processor, of running big endian, because I got the vibe that perhaps EMAS is big endian specific.
I got that, I think. The question was essentially that if you wanted to re-implement EMAS, why not do it on modern hardware? I did look at modern hardware, and that's the reason I started the compiler in 1989. But nothing came of that because I didn't have the time. And it's one of the reasons I got an IBM PS2, because the hardware is incredibly heavily documented. They're completely the opposite of many other systems, where you can find out absolutely everything about what every bit does. And I've got all the manuals for that. So that's what I did, but it never came to anything. I got this different post in the university and I didn't have time. And yes, modern hardware, quite a lot of it is big endian, and that will make life a bit easier. Although I think at that level, it would be certainly possible to make the changes to work it on little endian easily enough. My target was really not so much re-implementing it as resurrecting it in the spirit of the CCS. So that's why.
But what I'd like to see is
Two things.
software
It's
preserved
not-
in such a
Um,
way that
Firstly,
it
you
was
mentioned somebody
comprehended by
counting
other
line
people,
feeds and pages to
including
printers, and
experienced
Yeah.
nobody ever looked at the
in
statistics.
execution.
I went to work at Kinetic one day, and the secretary came up to me and said, "You're being charged for 2 jobs, each of several thousand pages.
Hmm.
If that was genuine work, that's okay. Or were you doing something for a secret society or something?"
Mm.
And I said, "Well, how far apart were those 2 jobs?" And they said, "About 5 minutes." I said, "Well, the printers can't print 5,000 pages in 5 minutes. Tell the accounting department to sort it out." I did eventually work out what had happened, and it was a complete mistake.
Yeah.
Second question, second thing, if you're trying to emulate one machine on another, and you just talk about endianness, do you have to implement the floating point hardware of one machine in the floating point hardware of another machine?
No, I implemented it in software.
Okay, so you
Yeah.
just wrote this.
I've done that, yes.
Very
I mean,
slow
all the IBM HFP emulation is actually in software. And there are tricky bits in the IMP compiler, because the IMP compiler has to evaluate floating point at compile time. Not much of it, but just a little bit to get floating point numbers in. And I had to transplant some of the code out of the emulator to use that, to do that, so that I could do multiplication and stuff like that. I took some ideas from the Hercules emulator from the IBM, which some of you will probably know about. But the problem with Hercules is it's actually operating on the registers in a very different way. And so some of the algorithms I stole partially, but then had to pretty well heavily modify. And some of it I just wrote myself. I also found it quite hard, actually, probably harder in some ways, to do the decimal arithmetic instructions. They are not easy to do, particularly when you remember that something like, I don't know, decimal add, or no, that's not a good example, but yeah, decimal add for the sake of the argument. I'm not sure it actually happens like this, but you have to do it for 32 bits, 64 bits, and 128 bits, because the 2900 has a variable size accumulator. It can be one of 3 sizes. And when you execute the instruction, it operates on the accumulator in that size. So you've got 3 emulations for the add instruction, 3 emulations for the subtract instruction, and so on. Then you've got the reverse subtract, and I just swap them around and then do the subtract.
Perhaps we can have one last question from an old friend of the society. Brian Randall has got his hand up. So Brian, would you like to ask your question?
Hi, not actually a question. I was going to comment that I had talked to Harry Whitfield beforehand, and I knew he was intending to attend. I was just going to say what a pity he didn't manage to make it. But I see that he had just arrived, and I thought the question of why don't you implement EMAS now on some small, incredibly powerful computer was one that should be passed across to Harry, knowing how busy he still is coding all sorts of interesting things. Harry.
Well, I think Bob's doing very well on his own, actually, and I've drifted off into other things, I think. It's interesting. The most interesting thing was that I think how the different versions of EMAS managed to maintain the more or less architectural structure of the original system in terms of mapping of files and the general way in which it worked. So I was really quite pleased to see that. I hadn't actually followed a great deal of the implementation on the 2900 or the IBM machines. It's actually more or less exactly 50 years since I left Edinburgh. And although I had some contact with the assessment of performance and things, one of my students at Groningen worked on that. And I did visit Edinburgh regularly, but I didn't actually follow really the detailed implementation of the 2900 systems. But it all appears to me to have gone through reasonably well. And I think a lot of it was probably due to the fact that it was written in a high-level language, and that made it much easier for people to understand the whole system. I mean, Peter Stevens, who's been mentioned, used to take listings of the whole system home in his briefcase, and he said there was still enough room for sandwiches. So that was.
I used to take them home as well. That's how I managed to read so much of it. Yes. Yeah. Yeah.
Well, as far as implementing it goes, I think it'd be quite a big job, and I'm not sure that, in a way, apart from historical purposes, it would be a system that people would now want to use. I think one of the perhaps weaknesses of the Edinburgh situation was that we didn't really, certainly in the time of the original implementation, have time to import different languages and the various tools that were available on the systems. I mean, one of the features of the Michigan terminal system that I knew quite well at Newcastle was that, as it was based very heavily on the IBM structure, a lot of the other software that people had written was able to be carried over quite easily. And at Edinburgh, there was a much more of a problem of writing things ourselves and not being able to bring things over. So anyway, that's just a comment. I was very pleased to hear the lecture, and I followed it all quite well, and it all seemed very familiar. So
Good.
Also offer just a comment. Do you remember perhaps several years ago in the Fellows Room at the Science Museum, I actually showed George 3 running on a Raspberry Pi.
I didn't get that.
David Holdsworth was saying he demonstrated George 3 on a Raspberry Pi at a CCS meeting a few years back. I think on that interesting note and the happy comments and the memories brought back, we should call it a day. Can we send good wishes to Brian Spohr, who's a regular attender here and is at present laid up in bed with a broken bone. We'll hope perhaps to see Brian again at the film show. I suspect it may take perhaps just slightly longer, so maybe won't be January, it's a Zoom meeting, maybe in February. Anyway, we send Brian our good wishes, and we conclude, Bob, by thanking you for a fascinating day, and we do look forward to
the Raspberry
EMAS
Pi.
running again. So thanks ever so much. It's been a lovely day, and we'll look forward to seeing hopefully many of you at the Christmas film show in a month's time. Thanks very much indeed. Thank you.
Thank you. Can I just say one last thing? I'm really pleased to see these people from Edinburgh, these names from the past. I'm sure there are more that aren't on the screen, and it's really great that you came. And feel free to email me afterwards if you want to say anything. You've got the email address on there, and the website has really got everything you want to know. So,